Okay, welcome back. So today we're going to finish chapter 25 finally. I spent a lot of time talking about magnetic fields. You know, I like magnetic fields, but it's very concept heavy, so it's good to have a lot of practice, all the different right-hand rules, right? I was just talking to some people in my office. I don't know if you realize there's two different right-hand rules, right? There's one where your thumb is the current and your fingers are the magnetic field. And you're using that when you're trying to find the magnetic field. And then when you're doing Lenz's law, your thumb becomes the magnetic field, and your fingers become the induced current, right? So did we pick up on that? So the thumb is changing roles. We're still doing the right-hand motion, but the thumb is now becoming the B field, and the fingers are becoming the current. And then the easiest way to remember which one to use is, well, whatever the straight thing is, make that your thumb, and whatever's curving, make that your fingers. It's really, that's all that we're doing. So when we're finding the magnetic field generated by a current, right, typically a straight wire, that sure you can bend that straight wire into a loop, but it's a straight wire, right? So you make the thumb the straight thing. And then for Lenz's law, we're trying to find the induced current, which we know is going to be clockwise or counterclockwise. And we know that current is produced by the induced magnetic field, which is going, either into the page or out of the page. So we'll make the straight thing the thumb, and the curvy thing the fingers. So we're switching those up. Okay, we're switching the roles. So, just making you aware of that. And then we started talking about qualitatively finding what that induced current is. Right, we were doing the right-hand rule to find the direction of it, is it clockwise, counterclockwise, and then we spent some time talking about Faraday's law, which is this statement right here, which states that the EMF or the voltage that causes the current, the induced current, it's equal to the change in the magnetic flux divided by the time it took to make that change. Where the magnetic flux is, so this is delta, which is final minus initial, right? And the magnetic flux is given as B times A times cosine of the angle between B and A. And so just as a review, the angle between B and A, well, the A here is the vector that points perpendicular to the area. So we want the angle between the B field and the area vector, which would be this angle right here. Okay, it's not the angle made with the area. It's not that angle. Pick a color. Right? It's not the orange angle. It's the green angle between the two vectors. Okay? So we did some calculations, and to kind of finish the thought here, right? This Faraday's law gives us the voltage. How do we turn a voltage into a current? You use V equals IR. So once you have the voltage, then you use I equals voltage over R to get the current. So that's the next step, right? To get the induced current magnitude, you take that voltage and you divide it by the resistance of the object that is hosting the current, right? Is it a copper loop, Is it, it's going to be a copper loop. It's going to be a copper loop. I guess it could be some other metal, right? Where the resistance would be given to you. Okay? So that's how we find the magnitude of the induced current. We find the magnitude of the voltage and divide it by the resistance of the object that's hosting the current. So we did this example here, the MRI bracelet, right? And we found what happens, if you're wearing a non-magnetic metal in an MRI, right? The non-magnetic metal won't be attracted to the magnetic field, but it will host a current. And currents make things warm, right? Your charging cable is warm when it's charging your phone, and your phone gets warm. Why is it getting warm? Because there's current flowing, and current when it passes through an object with some resistance, will generate heat, okay? So that bracelet is gonna get really warm and heat up, okay? It's gonna heat up, could potentially be dangerous, depending on how, much current is flowing through that bracelet. I think we saw it was like in the hundreds of milliamps, so it won't get too hot, but you never know. So, and then we kind of talked about eddy current. So that current that exists in the metal as a result of the changing magnetic field, we call that an eddy current. So that induced current, if it's a current inside of a metal, it's called an eddy current. So eddy currents are just induced currents that we've already been working with and calculating, but when it exists in the metal, it is called an eddy current. So I'm not going to have any problems related specifically to eddy currents. You're just going to be finding the current like you've been doing already, okay? But there's like some interesting applications, and then here's one I wanted to talk about. I don't know if you've heard of ExoMind yet. It's transcranial magnetic stimulation, but the brand is called ExoMind, and they're using it for all sorts of things to help with depression or anxiety or compulsive behaviors. And so if you want to look it up, it's called ExoMind. That's the brand. That's the company that turned this into a machine to sell to like med spas and stuff. So what is this machine? So this machine, the ExoMind, operates on transcranial magnetic stimulation. And so what is it doing? It's creating eddy currents in your brain. So your brain is hosting the current. And so what you do is you bring some kind of magnet near your head, and typically it's not a magnet, like a bar magnet, it's a loop that if you pass a current through a loop, you get a magnetic field, right? So we have this, it looks like a big circle, it's like a big black wand, and inside is a current carrying loop. And if we do the right hand rule with your thumb being the current, okay, you're going to see that if your current is going in this view from above counterclockwise direction, the magnetic field inside is going to point down. Up, right? It's hard to do the current that's in a circle with your thumb, but it's doable. And so you want to make sure that your fingers are firmly on the inside. So there you go. It's going to point up, right? My thumb is going in a circle. My fingers are pointing up when they're on the inside.
You said,
Mm-hmm.
You said this is the magnetic field.
Thumb. Oh, no. For this one, your thumb is the current, and your fingers will be the magnetic field. So if you want, you can imagine breaking this loop here and making it flat. And if you're doing that, then the current would go like this way, right? So if we're looking at the front part of the loop, our thumb is the current going like this, and then I'm going to make sure my fingers are on the inside of that current, right? My fingers are on the inside of the current, and you can see that my fingers are pointing up. So the magnetic field created by the wand that has the current loop in it is creating a magnetic field that is varying with time, pointing up. It's probably oscillating. It's honestly probably going up, down, up, down, up, down, okay, over time. And so you know that when there's a changing magnetic field, what happens? A current is induced, right, out of thin air, the induced current. And so that induced current is going to be in your brain because this current carrying wire that's creating the changing magnetic field is right next to your brain, right? So your brain is feeling these magnetic fields, but the magnetic fields aren't actually doing anything to your brain. What's happening to your brain and getting stuff to move is the current that's produced by the changing magnetic field. And that's the purple lines down here, okay? So we're creating currents in the brain, and all of your thought processes and everything, our brain works because of current. It's not electrons, it's positive ions like potassium. I'm trying to think of all the neurology. I don't really have a degree in neurology or anything, but there's ions in your brain that move back and forth that are sending the signals to different parts of the brain, right? So they're charged particles essentially. And so we're getting those charged particles to go into a region of the brain that maybe doesn't have a lot of activity. And, and the assumption is that you have a region of your brain with low activity, maybe that's the source of the ailment, whatever your ailment might be. And so, there's mixed reviews on if this is actually working for people or not. Could be placebo effect, I don't know. But it's an interesting application of eddy currents, and I just thought I would share that with you. So, we're going to close out this chapter by combining, we spent a lot of time talking about electric fields. We've spent a lot of time talking about magnetic fields. Now it's time for them to join together into an electromagnetic wave, okay? So we're going to talk about electromagnetic waves. And before we do that, let's bring up this little experiment for you, okay? Because I want to convince you that what is being created by a changing magnetic field is not just a voltage, it's actually an electric field. So that's what this first couple of slides is here to convince you. So let's suppose that we have a solenoid here, right, this guy, and there's a current flowing through it, and therefore it's creating a magnetic field in the center of the solenoid, right? That's what solenoids are used for. They're used for creating nice uniform magnetic fields in the center. And then you have just a loop of wire hanging outside of it. Well, what do we know if what happens to the loop if the solenoid current changes? If the solenoid current changes, then this B field is going to change its magnitude, right? If we increase the current, the B field will go up. If we decrease the current, the B field will go down. And so what happens if we have a changing magnetic field? We get that induced current, right? We get the induced current in this direction if the B field is pointing to the right and increasing. So let's just verify our right-hand rule for Lenz's law. So the first thing we do is we identify the direction of the magnetic field to the right. We identify if it's increasing or decreasing, and we're told it is increasing. And then we're going to use our thumb to be the induced magnetic field that opposes the increase or the decrease. So how do we oppose an increase? We create, or we don't, nature creates an induced magnetic field that opposes the increase by sending in a magnetic field in the opposite direction. So our thumb will be in that induced magnetic field direction, pointing in the opposite to the B field that's already there. All right, so here's B induced, and then you can see that it's going to create a clockwise motion as viewed from the right. Okay, clockwise as viewed from the right, which is that purple line. You can see if you're standing on this side, that's a clockwise motion, right, as viewed from the right. So, okay, so we got this induced current, but if you remember back from circuits, what causes an induced current? What causes a current? A voltage, right? Voltages from batteries, from power supplies cause currents. Well, what about the voltage is making the protons flow, right? The positive charges. What aspect of the voltage is doing that? The electric field that is created by the voltage, right? A voltage is a separation of charges, and you know that electric fields point from positive to negative charges, right? So wherever we have this voltage, we must have an electric field. And so what's happening here is the B field, the changing B field, right? The changing flux is producing a current, but what actually causes that current? What force pushes those charges around the loop? It's the electric field. So a changing magnetic field creates, in essence, an induced electric field. Sure, the current is a result, right? It's a result of the electric field being created. And so that's how we're connecting this to E fields and B fields. Like at the end of class on Monday, I mentioned electromagnetic waves are propagating in space from stars very far away because Like what's giving them that energy? Because there's a constantly changing E field that's creating a constantly changing B field that's creating a constantly changing E field, and then that's a propagation effect. And so that's why we can see light, like the stars in the sky. That's light from, I don't know, 100 light years away, right? How did that light get all the way here without energy? It's because it's constantly there's a constant propagation effect of electric fields creating magnetic fields creating electric fields. So that's the idea here. We're combining all of it together, and we're going to study the product of that propagation, which is electromagnetic waves. Okay? So here's another picture. This is the same picture, except we're looking down, we're looking basically at down the tube of the solenoid, except now the ring is inside the solenoid instead of being outside of it. But the geometry is the same, right? If you have a magnetic field pointing into the page and it's increasing, right? The magnetic field is increasing into the page. Lenz's law states that an induced magnetic field will be created to oppose that. So our B induced will be out of the page, and you can see our current will be in a counterclockwise direction. And that must mean that the electric field is also in that same direction, right? Because electric fields create forces that point in the same direction as the electric field for positive charges, right? When a positive charge is in an electric field, it's going to move in the same direction as the electric field, right? Because F equals QE. So that must mean that the electric field is pointing in the same direction as the current. The electric field is a vector, which means they can't be curved, right? So everywhere tangent to this curve is an electric field. There's only 4 shown here, but everywhere tangent to the curve is an electric field that is pushing those positive charges around in a loop. Okay? So now we have connected all the pieces of the puzzle. We know that changing B fields create E fields. Well, now we need to talk about the changing E fields creating B fields, right? So, electromagnetic wave is what's produced, right? Because the electric and the magnetic fields sustain themselves by constantly changing and producing the next. So, we don't talk about changing E fields, do we here? They kind of gloss over that because it gets a little bit crazy. So you just know that changing E fields create B fields and changing B fields create E fields. In the other book, we talk about the induced electric field. So creating B fields. So what we're going to do is we're going to dive into the properties of electromagnetic waves. And so I don't know if you've ever heard of the term particle-wave duality. It's a very cool term. So what we're going to talk about is that electromagnetic waves, they can behave like waves, as in their name, and they can also behave like particles, okay? So some broad aspects of properties of an electromagnetic wave is that it's a transverse wave. So what does transverse mean? Transverse means that the direction of the velocity of the wave is transverse, or perpendicular is another word for transverse. That the velocity is transverse to the electric field and the magnetic field that create that electromagnetic wave. Okay, and we'll talk more about those directions, but that's what the meaning of a transverse wave is that its motion is perpendicular to the thing that makes up the wave, which is the E field and the B field vectors, right? Because it's an electromagnetic wave. The speed of electromagnetic waves is fixed. Okay, if it's moving through vacuum, you probably remember that from the beginning of this course, right? And then as it travels through glass or through something else, it slows down. But in space, in the vacuum of space, it's going to move at the speed of light. Well, guess what? This is a really neat way to write the speed of light. It's with your favorite constants. Okay, 1 over the square root of your 2 favorite constants gives us the speed of light, right? This was the constant that we used for electric fields. This is the constant that we used for magnetic fields. 1 over the square root of that gives you the speed of light. So that is why we use the constants. They're all connected. They're not arbitrary or random. So that's an interesting result. Okay, the person who figured all this out was James Clerk Maxwell. So I don't know if you've ever heard of Maxwell's equations. He is the author of all the beautiful symmetric equations that describe the motion of electromagnetic waves. And basically, most of the technology that we use today is because of James Clerk Maxwell. So like Wi-Fi, this projector working, charging, right? Wireless charging, right? Now we don't have to plug in our iPad or our phone anymore. We just set it on a wireless charger, which uses induction to charge your device, right? So he's responsible for all of that. So here's a picture of an electromagnetic wave, a transverse wave, right? Because its velocity direction is transverse or perpendicular to the things that are making up the wave, the E field and the B field. And the other aspect is that the E and the B are perpendicular to each other as well. So a relationship here is born. Basically, the E field is always going to be perpendicular to the B field, which is always going to be perpendicular to the velocity direction. They're always going to be perpendicular to each other. And you also might have noticed this sinusoidal kind of behavior here. So both the E field and the B field can be written in terms of a sine or a cosine function. And that those two are in phase, right? So wherever there's a peak in the E field, there's going to be a peak in the B field. So they're in phase. So those are some properties of electromagnetic waves. So another thing that we can extract from this is that the constants, the magnitudes of the E field and the B field are related also to the speed of light. And you can actually set this equal to 1 over square root of mu naught epsilon naught. And you can also see that you can express the E field in terms of the B field and vice versa. So for sinusoidal waves, recall from earlier that the speed of the wave, which may or may not be the speed of light, right? Depends on if the wave is moving in an object other than vacuum. So that's why we use V, because it could be anything. It's related to the wavelength of the wave times the frequency of the wave. Okay, so the wavelength of the wave, just a reminder, the wavelength is the distance from one point, right? This is the increasing point to the next. Could also be, that's if you're using the zeros. You could also say it's from peak to peak, okay? So wavelength is one entire, length of a wave. The frequency would be, can't see it in this picture because this is at one moment in time, right? In order to see the frequency, you need the time dependence graph, right? This is the distance dependence graph. So to pull out the frequency, you need a time dependence graph, okay? But we don't have it pictured here. Just as a reminder. Okay, and so here's some more properties of electromagnetic waves. We are gonna call them plane waves. And what a plane wave means is that everywhere in the plane of an electromagnetic wave, the values will be constant. So here I had a picture of one electromagnetic wave, right? This is one. In this picture, we have 4, okay? There's 4 electromagnetic waves. So imagine them all coming from a source like maybe the sun, okay? The sun produces a bunch of electromagnetic waves, and we'll talk about that in more detail. So what we're saying is when we say that an electromagnetic wave is a plane wave, we say that if we stop the electromagnetic wave and we kind of like slice through it, that the magnitudes of E will be the same everywhere in that plane, and the magnitudes of B will be the same everywhere in that plane. Okay, so like here we took a picture we stopped it, that's kind of what I meant by stop, is like we took a picture at time t equals 0. Okay, here's another picture, another snapshot, right? Everywhere the magnitudes are equal. Here's another picture, here's another picture, here's another picture. Okay, so this would be like our time dependence graph, right? We're seeing how the vectors change their magnitude with time. And they're gonna be equal everywhere. So that's what a plane wave means. And so if a plane wave were to move towards you, okay, or move past you, you would just see a uniform oscillation of all the electric and magnetic vectors of the wave, okay? So that's all that a plane wave means. And these pictures are just zoom in of that larger image. So I'll skip those. So we showed you in the graph, right, that the E field and the B field look like sinusoidal functions. So this is the function that we use to describe the magnitude of the E field and the B field at any time and at any position, okay? Right, because there's two parameters that determine the strength of that E field or B field. Where it is along this picture, let me scroll back real quick, right? What position you are in. So like right here, I know that my E field and my B field are a max at x equals 2 or something, right? And then time, right? This is a snapshot at one time. So time is the other variable, right? These things are oscillating with time. So if I were to keep an eye only on x equals 2, I would see that E field vector go to 0 and come back, and go to 0 and come back, and go to 0 and come back. It's harder to picture that, right? That's evidenced by this series, right? This is a time dependent. So you can see the oscillation of the E field. It's big, it shrinks, it's 0, it goes negative, it gets super negative, and then it starts all over again, going back that to the left. Okay, so the position and the time are both parameters that you need to know in order to determine what the amplitude of the E field or the amplitude of the B field is. Okay, and they're related by sine functions. So, I mentioned that the E field and the B field and the velocity are all perpendicular to each other, right? So if we were to place them on an XYZ axis, the relationship we would see is that if the electric field is in the X, and if moving in the X, so if the velocity is in the X and the electric field is in the Y, then the magnetic field must be on the Z. Okay? And then here's that relationship again. The ratio of the amplitudes must equal the speed of light. And the speed of light also equals 1 over the square root of u naught epsilon naught. A result of this relationship is that the E field must be a lot bigger than the B field. Right? Because if you're taking a number and dividing it by another number and your answer is a gigantic number like 300 million, right? 3 times 10 to the 8. Well, that means the E field must be gigantic, right? Or the B field must be really small, either one, because you're dividing by a small number. So another wave property, right? So we're talking about the wave properties of electromagnetic waves. So here's another wave property that we actually use all the time. And this is called the polarization of the E field. So when we talk about the polarization of the E field, what we're talking about is what direction does the electric field of the E field point. If we know the direction of one of those 3, then we know the directions of the others, because they all fit into a right-hand rule. Your last right-hand rule, how excited are you? Your last right-hand rule is the relationship between E, B, and V. So you can see that if you take E and squeeze it into V, then your thumb will be in the direction of the velocity. And that's always your right hand. So that's the order it must be in. E, sweep it in V, gives you the velocity direction. Okay? And so that's why we only talk about the direction of the E field, because if we know the direction of one of those vectors, then we know the direction of all the rest. So by convention, we've chosen the electric field as our guide. So the plane of polarization is the plane that the electric field lives in. And if the electric field is parallel to that plane, then we know that the electric field is vertically polarized. Okay? The electric field only exists in the y-axis, parallel to the y-axis. Okay, so we'll say that that's vertically polarized. So here's some other directions that the E field could exist. Okay, the E field could be on the y-axis like we just saw. Okay, which would make the B field on the Z and the velocity direction in the X coming out at you at the page. But the E field could also be in the Z direction. Okay, and then that would make the B field in the Y and the X coming out of the page, right? Still. And then the E field could be in between the Y and the Z, okay, at some angle with respect to the Y-axis. So we would call that, an angle, a polarization angle, okay? Horizontal polarization would be E field on the Z, and then vertical would be E field on the Y, okay? So light in general, when light is produced by one method or another, typically light is produced by electron transitions from high orbital to low orbital or high shell to a low shell, right? When an electron jumps down, it releases a photon, which we're going to talk about, right? It releases a burst of energy, and the frequency of that energy is typically in the visible or UV spectrum. And so that's what the sun does. And when it does that, whenever you have a natural source of electromagnetic waves, there is no preferred polarization direction. We as humans can modify and create polarized light. But when light is created by a natural source like the sun, or even an incandescent light bulb like that bright one, I think these in the ceiling are LEDs, because we've updated almost all of our light bulbs to LEDs, but the really, really bright one, this one that's spotlight on me, actually, if I look at it, all I see is that, are still probably incandescent. So the light from an incandescent bulb is created by just passing a bunch of current through a wire that glows, right, because it gets super hot. And that's a natural source of light, and so the light coming out of it is not going to have one electric field direction nailed down. It's going to be random, right? It can exist equally in all directions. So we call that unpolarized. So an unpolarized wave would look like this. It would have E fields everywhere equally, right? And so what we can do is we can polarize. Maybe you've worn polarized sunglasses, right? Polarized sunglasses make the, what you see very dim. And you're going to see exactly why it does that. So before we talk about polarized sunglasses, let's talk about the energy of electromagnetic waves, okay? So we have already talked about the intensity of waves before. We defined them as a power over an area. And just a quick reminder what power is. Power is an energy over time. Okay, so intensity is an energy over time divided by an area. Okay, so that's going to come up again. We're going to need to know that. The intensity of an electromagnetic wave can be expressed in terms of either the E field or the B field. All you got to do is switch around some constants. So the intensity of electromagnetic wave, you can express it either way, as long as you know one magnitude or one amplitude. Okay. And so how does it go in between? Because you know that E divided by B equals C, right? So you can just, if you know E, then you know B, because Everybody knows what C is. So that's how you can switch between the two. So when we talk about intensity of a wave, okay, we've previously said that electromagnetic waves act like plane waves, okay? But when we talk about the intensity of an electromagnetic wave, we're actually going to treat the waves as spherical waves, all right? So when do you use plane wave? You use electromagnetic field as a plane wave when you are very close to the source. I'm sorry, you're very far from the source. Very far from the source of the wave, okay? That's when it acts like a plane wave. But when you're close to the source, let's say this light bulb right here, you can imagine, I'm sure, right, if I turn off all the lights and left that one on, that the light you would see the light back here, right? You would see the light everywhere. You wouldn't just see it directly on me. It would be glowing and you could see it in other directions. And that's because when you're close to the source, light behaves like a spherical wave where it starts off at a point and then it spreads out equally in all directions like a sphere, okay? So whenever we are calculating the intensity of an electromagnetic wave, we're going to treat it as a spherical wave, okay, which spreads out from a point. And when we do that, we can write the intensity as the power of the source, something like a 50-watt light bulb, you know, something in watts, right? The units of power is a watt, divided by the area of what? Surface area of a sphere, right? Because we're treating it as a spherical wave. So this is the surface area of a sphere, 4 pi r squared. So let's put this to practice. If we want to double the intensity of an electromagnetic wave, what should we do to the amplitude of the E field? Like what factor should we increase the E field by? So let's go back and look at the equation for the intensity of an electromagnetic wave in terms of the E field, and that's this guy right here. Okay, so if we want I to double, so if we want 2I, what do we have to do to the right-hand side of the equation as far as the E field amplitude? We need a 2 to come out of this equation. How would a 2 come out? It would come out if we had, we wanted 2 to come out in the top, right? Square root of 2. I knew that. It would come out, we would get a 2 out if we had a square root of 2 on the inside, right? Because the amplitude, increase the amplitude by square root of 2, and then you square it, you get your factor of 2. Does that make sense? Kind of like a reverse way of solving the problem. So a square root of 2 increase in the electric field amplitude will give us a factor of 2 difference, and a square root of 2 is 1.41. Plug that into your calculator, it's 1.41. Let me grab my calculator just to have it out. Okay? So in summary, this is a summary of the wave-like properties of an electromagnetic wave. E field and B field are perpendicular to the velocity direction. The amplitudes are related to C. Okay? Intensity given. Okay? Power over area. So let's do one of these example problems. Let's do this one since this one has all the solutions written down. Okay, so talking about our microwave. Okay, a microwave works because of electromagnetic waves. There is an object called a magnetron inside of your microwave, and it has a magnet, right? An electromagnet, which is a coil wrapped around a strong magnet, and it's producing electromagnetic waves at a frequency of 2.4 gigahertz. Okay, right? This is a frequency. Giga is 10 to the 9. Okay, so it's 2.4 times 10 to the 9 hertz. That's the frequency of your microwave oven. And the intensity of those waves is 5 kilowatts per meter squared. So I is 5 times 10 to the 2 watts per meters squared. The question is, what is the strength of the electric field and the magnetic field? Well, we know that there's a bunch of constants, C epsilon naught, E naught. Okay, we can easily find the electric field amplitude here because we know C and we know E, epsilon naught, right? So we can easily solve for E naught. Two I over C epsilon naught square root. Okay? I'm not gonna put the numbers in, there's the formula, right? It's a pretty basic manipulation of the formula. And then to find the B field, well, you know that E naught over B naught equals C, so to find the B field, you would take E naught and divide it by C. Okay, so that's how you would solve it. This is mainly a language problem, right? Just being familiar with the terminology. And so that's what is done, right, in this, also this example. So let's talk about how we polarize things and why we do. Okay, so we can create polarizing filters. And polarizing filters are made up of polymer chains. And these polymer chains absorb electromagnetic fields. And specifically, they absorb E fields, okay? So the polymer chains are here in the blue lines. And so they absorb electromagnetic fields. They absorb almost every direction of electric fields, except the direction perpendicular to the polymer chain. So the way a polarizing filter works is there's our unpolarized light right here, right? Because our E field is pointing in all directions at the same time. So it's unpolarized, right? There isn't just one direction. It's gonna pass through the polarizing filter, and the polymers are gonna grab every vector that points in a direction that is not perpendicular to the polymer chain. And so the only vector direction of the E field that's gonna survive the polarizing filter will be the perpendicular to the polymer chain, which is parallel to the polarizer axis. So you see the polarizer axis is defined as the axis that's perpendicular to the polymer chain. And so, in other words, what we could say is that the polarizer only allows vectors parallel to that polarizing axis to pass. But what's physically happening is that the filter is absorbing every direction but that one. Does that make sense? So the filter is absorbing every direction but the direction perpendicular to the polymer chains or parallel to the axis, the polarizing axis. Okay? So this filter is going to reduce the intensity of the electromagnetic wave. Okay, why? Because it's robbing almost all of the vectors from it, right? So that's why we use polarizing filters. So that's why polarized sunglasses work better than unpolarized sunglasses, because you have this extra blocking effect. You don't just have color blocking the light. You have color plus these polymers that absorb electric fields blocking the light. So qualitatively, that's what I explained is basically in this paragraph, right? Qualitatively, what's happening is only the parallel component to the polarizing axis is allowed to pass through for the E field, okay? So this is gonna change the intensity of the light. Obviously, it also changes the electric field of the light, and we know that intensity and electric field are related, right? By squared and a bunch of constants in front of it. So if we look at the electric field, it's a vector. So if we want to know what component of the vector passes through, then we're going to use our vector tools, right? So let's say that we have an E field vector that kind of points, off the y-axis. And we're going to pass it through a polarizing filter. And the polarizing filter has its polarizing axis right here. Then the only component that's going to pass through is the component of E that is along this direction. And you can see that using vectors and right triangles, that magnitude is E naught cosine theta, right? Because this is the adjacent to the hypotenuse and to this angle, right? So, So electric field wise, what the polarizing filter does is it reduces the magnitude of the E field vector because you're multiplying it by a cosine theta, right? And cosine theta is usually less than 1 unless theta is 0. So it's like you're scaling it down. And so, we don't see electric fields, we see intensity. So how does that relate to what we observe? It makes it less bright, right? The intensity decreases because intensity is, a bunch of stuff, 1/2, right? Intensity is 1/2 epsilon naught E, right? So intensity is proportional to the square of the electric field magnitude. And so that means that the incident light that's transmitted past the polarizer is going to get smaller, right? It's going to reduce in intensity by a cosine squared. So this is called Malus's law. So Malus's law tells you how the intensity of light changes when it passes through a filter. So this is why when you put on polarized sunglasses, everything looks dimmer, right? So it looks dimmer because that unpolarized light is getting stripped of most of its electric field vectors. Only one survives, one direction survives. Well, one axis really, two directions, right? One axis. So Malus's law can be demonstrated with two polarizing filters because the intensity change from unpolarized to any polarized direction is actually fixed. So whenever you go from unpolarized to polarized, the intensity actually only changes by 1/2. So for I unpolarized to I polarized is only changes by 1/2. Doesn't matter what the axis is, okay? And the reason for that, we don't really dive into it, but it's an average, right? So unpolarized light has an E field in every direction. So the average intensity goes down by 1/2. But then when you start with a polarized light, right? This is polarized in some direction off the y-axis, and then you pass it through a second polarizer, well, then that's when you see the Malus's law in action. That's when you get the cosine I at the analyzer will equal I after the polarizer times cosine squared theta. That's the Malus's law, okay? So the Malus's law applies to already polarized light getting repolarized, okay? The unpolarized to polarized is just goes down by 1/2, and that's just something you have to remember. So Malus's law doesn't show you that. It's an argument about averages. Okay, so that's just something you need to remember. So if my demo guy was here today, he's unfortunately ill. I would have a bunch of polarized demos to show you, but this is essentially what I was going to show you. You can see that if theta is 90 degrees, right? Cosine of 90 is 0. you can actually use two polarizers to completely black out and absorb all of the light. So here's a picture of that. Here's a polarizing film, and this red line denotes the polarization axis, okay? We're gonna put another polarizer in front of it that is 90 degrees to that, and you can see that where they overlap, you see absolutely nothing. And why is that? Because I equals I naught cosine squared of 90, and cosine squared of 90 is 0. So the intensity of the light after passing through both will be completely squashed. And all that energy gets absorbed into the polymer of the film. So we call this arrangement crossed polarizers. Cross polarizers are helpful. Let's say that you have light that has two polarization directions and you want to get rid of one of them. Well, then you would want to cross the polarizers to be 90 degrees with respect to that one, and you would eliminate that one but allow the other to pass through. So we use polarization a lot to analyze images. So this is an image of teeth. And this, I can't remember the name of this technique, but essentially you're scanning the teeth with polarizers, and whenever there is a change in polarization, you get a different color. So you kind of match the color to the polarization direction of the light. And that helps you identify regions where the tooth enamel has changed into something other than tooth. Like when, bacteria eats away at your enamel is no longer crystalline. It becomes kind of like a random mush of bone, I guess, or whatever is made up of, whatever the teeth make up the teeth, right? And that is going to affect the polarization of light as it reflects off of the teeth, right? This image is created because we shine light to the teeth, it hit the teeth and reflected back to the camera or the detector, okay? So if you put a bunch of polarizing filters in there, you can catch what polarized angle the reflection gives you, and it can tell you the property of the material, in this case, the teeth. So it has a lot of application. Polarizing filters have a lot of application in imaging. So finally, let's talk about the sunglasses, right? Obviously, one purpose of sunglasses is to reduce the amount of light that you see, so it's not so bright and you're not overwhelming your iris and your retina. So what it will also do is eliminate glare, right? It's good for driving. And so what is glare? Glare is like really bright light, right? It's so bright that you can't see anything around it. And so it's important to not see glare when you're driving, because you don't want like light reflecting off the back windshield of a car to blind you, right? So you put on your polarized glasses and it eliminates that. So how does that work? Well, we can polarize light by passing light through a filter, right? But light also gets polarized upon reflection. And so when light from an unpolarized source gets reflected off metal, that reflected light gets super polarized. And all of that polarization pointing in one direction is going to create a very intense source of light, and that's going to be our glare. Well, the polarized glasses, when you put them on, they're going to eliminate most of that light, and you're going to be able to see a lot clearer. You're going to eliminate most of that intensity. And specifically, reflection produces horizontal polarization. So it doesn't matter what the surface is. The reflection of light will cause horizontal polarization. And that's why your glasses are always vertically polarized. So let's talk about Malice's law, just a quick application here. So let's say that we have vertically polarized light coming towards us. So behind this filter, we have polarized light in the vertical direction, okay? I'm not drawing it all the way because it's behind the filter. So then it's gonna come towards the filter, and what's gonna happen is the light is gonna become polarized in a new direction along the axis of polarization of this polarizer, which we're told is right. Okay, let's see. This is the polarizing axis, right? After passing through. Yep, this is the polarizing axis. So after the light passes through, it's going to be pointing in this direction. Okay. And the question is, how does the intensity change? So if this angle is 45, well, then this angle must also be 45, right? And that's the angle between the polarizing axis and the electric field. So we care about this angle right here. That's our theta. And so I equals I naught cosine squared 45. Our initial intensity was 1,000. So we're gonna scale it down to, well, cosine of 45 is square root of 2 over 2. And then that thing gets squared, right? So it becomes 1/2, doesn't it? Because the top becomes a 2, the bottom becomes a 4. So nothing too crazy. Things are slowing down, right? As you can tell, we had a peak with the electric fields and the magnetic fields. I think people are liking a little more conceptual. And now we're getting real easy. So do this one at home so you can finish this lecture. So now we've finished talking about the wave properties of light, okay, ending with polarization. So now we're going to look at the particle or the photon model of light, okay? Photon is a particle. So electromagnetic waves have a particle-like nature. The particle part of the electromagnetic wave is called a photon. So that is a fictitious particle. It's not a real particle, not like an electron is real, okay? Protons are real. Photons are not real, but I guess they're real and not real at the same time. We can get real philosophical here, okay? So we can measure photons, we can measure the energy of a photon, but we can't really grab a photon and, like we can an electron. So how do we know photons exist? Well, I don't know if you've ever taken a really dim picture before, okay? You would think that if electromagnetic waves are waves, that if we took a dim picture, the whole picture would look dimmer. But when you take a picture without a lot of light, you actually see speckles, right? You don't just see this whole picture getting dimmer. You start seeing the speckles. The speckles are evidence of the particle-like nature of electromagnetic waves. Because, I don't know if you recall when we talked about how cameras work, cameras are made up of an array of little boxes that all absorb electromagnetic energy. And so only some of the boxes are absorbing that energy when the light is low. And that is showing you that the wave is not spreading over all of those little parts, those little boxes of the CCD, right? Only the particles are actually only hitting some of them, and thus producing the grainy picture, right? The little dots. So this is just one example of, why we can talk about electromagnetic waves as particles, because we actually can see that it does behave like particles a lot of the time. So we use the photon model, and the postulates of the photon model is that instead of treating electromagnetic waves as waves, we treat them as a source of particles called photons. And these particles don't have a mass, okay? They're massless. And they are discrete, meaning their energy levels have specific discrete values, like 1, 2, 3, 4, okay? And there's no continuum like 1.1, 1.2, 1.3. So that's what discrete means. And that photons travel at the speed of light, the same speed that a wave does in a vacuum. The photon model, this discreteness, okay, is given by the energy of each particle. And this is where you can see how only certain values can exist. It's some constant called Planck's constant multiplied by the frequency of that wave. So H is the Planck's constant, also called the universal constant, and its value, it's very, very small. Okay, 6.6 times 10 to the minus 34. So electromagnetic waves only come in discrete chunks in energy, or energy quanta, we like to call this, energy quanta. Quantas of HF. So we're counting in units of HF. Instead of 1, 2, 3, it's HF, 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 where F can be a different number. You know, F can be, we're gonna talk about what F is. We're gonna look at the spectrum. So the third postulate is that if we superimpose enough photons, then that's where the wave characteristics actually start showing up. So electromagnetic waves will behave like a particle if there's only a couple. Electromagnetic waves will behave like a wave if we have a whole bunch of photons. Okay, so there's kind of like a statistical analysis that determines whether you're going to treat the wave as a particle or as a wave. So this is kind of like a little bit of a throwback. So if we have an analog cell phone, so like the oldest cell phones, everyone, because there weren't a lot of cell phones, we were all on like one network, right? And the band at which we were talking to each other was a frequency of 850 megahertz. Now we have 2G, 3G, 4G, 5G, right? What does all those G's mean? We're changing the frequency that we're operating at to communicate wirelessly. So newer cell phones operate around a frequency of 1950 megahertz. And the reason why it's changed is because we've gotten better at coding information in higher frequencies. And higher frequency waves will travel farther than lower frequency waves. So, but let's talk about now the properties of a wave with different frequencies. So how do we compare the analog to the digital? Okay, the analog being 850 megahertz and the digital being 1950 megahertz. So we're comparing the wavelength and the energy. So to look at the wavelength, we're going to use C equals lambda F, right? So the higher the F, the lower the wavelength, right? Because they both need to be multiplied together to make C. So if F goes up, then wavelength must go down, right? So the higher frequency will have the lower wavelength. But the energy of these particles, these photons, depends on the frequency. So the higher the frequency, the more energetic, or the higher the energy of each photon that represents it. So, in other words, higher frequency, lower wavelength. The higher frequency, what are we comparing? Analog, digital to analog. Okay, so we're saying, what is the digital to analog? So the digital has a higher frequency and a lower wavelength, a shorter wavelength. Okay? Or shorter wavelength instead of lower. Okay? So that's what we showed. Higher frequency, shorter wavelength. So now let's talk about the properties of power and intensity in relation to wavelength. So radio towers emit electromagnetic waves, right? which transmit communications. So let's say we have two radio towers emitting 50-watt signals. One 50-watt signal is an AM signal of a frequency of 850 kilohertz, and then there's also an FM signal of a different frequency, 885 megahertz. So which one has more photons per second? So we're going to have to break this power down into what it is. So power is an energy over time. And so what is the energy here? This is the energy of the photons that are making up this electromagnetic wave, right? Because we're treating the wave as a particle. So the energy is in quantas of HF, which there's some number of them, right? For 50 watts, you're going to need a bunch of photons, not just one photon, to create that amount of energy per time. So our time will be seconds. So we're looking for photons per second. So we're basically isolating this part, N over S, right? Number per second. Photons per second. Number of photons per second. So which power of frequency will give us the biggest N? So we have 50 watts equals NH, we'll say FAM over time. I'll just say time, okay? And then we have 50 watts equals NHFM frequency over time. So our AM frequency and our FM frequency are, so one's bigger than the other, right? So we can actually probably stop here and kind of look at it more just qualitatively. So our FAM is smaller frequency, right? Because 850 kilohertz is 850 times 10 to the 2 hertz. Where 85 megahertz, your prefixes are going to be important here for this chapter, 85 times 10 to the 6 hertz, right? So 85 megahertz is bigger frequency. So if we have a smaller frequency in the AM, in order for this 50 watt to remain true, then this guy must be big, right? And then the same argument can be made here. If this guy is really big, then in order for this number to stay 50 watts, then this must be small. So the AM signal is going to have more photons per second than the FM, right? So the AM signal will have more photons per second. Good, we're doing good. So let's skip this guy since we have all the solutions here. Okay, it's very basic application. So it's common, maybe not for what you guys are going to be studying, but in physics, we like to use EV as our energy unit. So if you remember EVs, right? EV is a unit of energy. It's called the electron volt. It's simply the charge of an electron multiplied by the voltage it passes through, okay? So we can use EVs to describe the energy of photons, mainly because if you calculate the joule value, it's going to be something insanely small, right? It's going to be like on the order of 10 to the minus 20 or something, right? If you use EV, the numbers you're working with are a lot more, digestible, if you will. So these are some typical EV values of some atomic and molecular processes. So this is like a spectrum, right? So we're actually the last thing we're gonna talk about is the electromagnetic spectrum. So let's talk about all the different types of electromagnetic waves and how they are related to each other, right? We looked at AM, FM. So we're gonna look at X-rays. So we have two different ways to look at the electromagnetic spectrum. They can behave like particles, they can behave like waves, all right? So you might have noticed that for the electromagnetic waves, we speak of radio waves, but we talk about X-rays also as electromagnetic waves, right? So we're using the ray or the wave. So typically we use ray when the wave is behaving more like a particle. And we use wave when, obviously, the wave is behaving more like a wave. All right? So, this is where those guys live on the electromagnetic spectrum. So when you have very high energies and very small wavelengths, you're going to get particle-like behavior. And so those types of waves are gamma rays, which are produced by heavenly bodies, stars, okay? X-rays also produce a lot in outer space, but we can make them here. We make them all the time to do imaging. Ultraviolet, now we get into the visible light spectrum. And then we're going to go down to infrared, which is like heat. So this is like the wave of heat. And microwaves, radios, AM. So the microwave region is like kind of where our cell phone is. Our cell phone is around here. Okay, and then you have radios and, TV channels when we used to transmit TV via electromagnetic waves in space. Now we use cables and stuff. So wave-like behavior happens when you have large wavelengths and little energies, okay? And just as a reminder, the frequency, right, is inverse to the wavelength. So here where you have a small wavelength, you actually have large frequencies. And here you have small frequencies. So this kind of just explains what I just, the electromagnetic spectrum in terms of wavelength and frequency, okay? Actually, they don't mention frequency here, but I did. And EVs. So an important property of electromagnetic waves is the value of the current does not dictate what electromagnetic wave is produced. The only thing that matters is the timing, the frequency. So if I have a current that is oscillating at a frequency of 50 hertz, that's going to produce an electromagnetic wave of 50 hertz. If I have a current that's oscillating at a frequency of 1,000 hertz, and that's going to be the frequency of the electromagnetic wave. The magnitude of the current does not matter. Okay? And then antennas, we're not gonna talk too much about antennas, but antennas are essentially dipoles that are both producing electromagnetic waves and sensing electromagnetic waves. Don't worry too much about antennas. I think the last thing I want to talk about was the spectrum, okay? The electromagnetic spectrum. Everything else is just qualitative, okay? So that's going to wrap up chapter 25. This stuff you'll need for the homework, but it's not going to be on the exam. So let's do this. Let's stop right after the spectrum. That's exam. Here we go. Right here, basically. Exam is up. Exam is everything above, and then stuff you need for the homework. You should, go cycle through. There's just a couple of questions. Okay, cycle through the rest of that. Okay, well, let me know if you have any questions, and then the exam is on Monday. All right.